Hi guys. I just spent, so now it's Wednesday, it's 9 p.m., huh? I've just been working for something like 3 to 3.5 hours, plus all the other time is spent trying to work on this lab. And I'm telling you, man, wow. They really did, this lab really is in serious need of a rewrite. Okay, so I'm gonna like summarize stuff that I've already gone over, and then the big deal we're waiting on is part two, but it turns out part two is straightforward. So Archimedes' principle is basically that an object placed in a fluid will displace or take the place of the fluid, and most of the time it's water. The weight, which is, remember, also a force of the displaced fluid, is also the force pushing up on the object, F buoyancy. So that's equation 2. And give me a minute. No. Ha ha ha. That's funny. I see. I looked at, because I reversed the order, so that's where I saw the 2, huh? So that means it's this equation. So that's always true. And so if we, so let's see, the weight of the display, yeah. Now, if the object is completely submerged, then of course the displaced water is equal to, the volume of the displaced water is also equal to the volume of the object. So then these two equations now become V object in both of them. And then it allows me to divide the two, and then lots of things cancel, and I'm left with this. So in part one, we're going to test this, and we're going to do this by, and in fact, it turns out what we were supposed to do is calculate volumes. But let's just charge ahead in what we did do, and I'll show you what we're supposed to do. So what we're going to do is we're going to get the weight of the object, which is the brass. We're going to find out what's the buoyant force and multiply by the fluid, and we should end up with the density of the object, which is in this case the piece of brass. Now, we need to understand the definition of the buoyant force, at least in terms of how we're going to measure it. And we call it, we have a scale where and when I see scale weight, just means what we read, scale weight. So in this case, the scale weight, which is, and I'm playing a little loose here, and of course weight is in newtons, but this thing is going to measure us a mass of an object, and if I multiply by the acceleration of gravity, I get the weight of the object. But what's folded in here, that what's the only force downward on this object is the force of gravity, its weight. So that means that when I put some equivalent mass over here that has the same weight, that mass is going to equal the mass of the object. So in this case, in the nomenclature we're using, we're saying that when we do this scale weight with the object, we're going to call it the mass of the object, which seems kind of duh, but it's just because we need to have a separate nomenclature from when we weigh the object when it's in water. So in this case, what we see, the scale weight, is going to be the actual weight of the object, but the buoyant force is going to push up on it. So we're going to actually measure a mass, because the scale weight then, if we divide the scale weight, if we divide these forces by grams, that is actually what we're going to see on the scale. So it's not equal. Not grams, by the acceleration of gravity, it's going to be mass. But wanted to keep it in terms of forces. So then at the end of the day, since these two equations define whatever it is, the weight we're measuring, and F buoyancy is in there. So if I simply take the mass we got here, subtract the mass we got there, and multiply it by G, that's going to be WG like we got here, and minus a number that is WG minus FB, and then of course this becomes WG minus WG plus FB. So that leaves us with the buoyancy force. Now we went on to this, and in fact we didn't really use the force of the buoyancy. But anyway, well, let's finish the thought here. So we have the mass of the brass, we have the mass of the brass in the water, and we can go ahead and we can then calculate the force of buoyancy here. We plug. I put in the 1,000 grams per kg because we're going to use 9.80 meters per second squared, and that has newtons are in kg meters per second squared. So then we end up with 4.421 newtons, and then this should also equal the weight of the displaced H2O. So then if we take we know then this is equation, hold on. This is equation 2, which is always true, which is actually a definition. Because if we take the density of the object and multiply it by the volume, we're left with mass. So rho times volume equals mass, because we see kg meters cubed per meters cubed times meters cubed is kgs. And once again, if we multiply it by the acceleration of gravity, we're going to get a weight, which is in newtons. So that's what I'm here. I'm also getting a weight in newtons of the brass, the buoyancy force on the brass. But we know, if we assume Archimedes' principle is correct, then that should also equal the weight of the water. So that means then if we multiply the rho of the water times the volume of the water times the 9.8 meters per second squared, we should get the same. We should get 0.421 newtons. So then we can solve it for the volume, and I came up with 4.30 times 10 to the minus 3 meters cubed. And this is then, I just convert it to centimeters cubed, and it's 43. And if you look at our spreadsheet, it turns out that that's what we got by measuring with the calipers. Now, what we were supposed to do is compare that to, this is the one, volume Archimedes, compare that to the one we used with the calipers. And they look good. They're exactly the same. What's weird is that I would have totally expected the plus minus here to be much smaller. But it's not. It turns out that when we determine the volume using Archimedes, we got a much smaller plus minus. Oh well, that's not a problem. And I think I'm going to address that right here. Yeah. No, it doesn't matter. So I guess the point is that that's as far as I went with this, because we didn't do this, and you shouldn't worry about it. What we did do is we weighed the object, we got its mass, and then we could multiply that by g to get its weight, and we did it's all we did in the spreadsheet already. and then we calculated an F buoyancy, and then we multiplied by a known value of the water, and we end up with here 8.45. And give me a minute. What did I do? We actually, so first of all, we just calculate straight row object by mass by the volume, but we didn't use that. And then we calculated row object using this equation, and that's what we got with a plus minus, and we compared that to the accepted value, and using there's this business at the end, the handwritten stuff at the end of the manual, which basically you don't even have to deal with, because this part we already did all that together, and then this part is they wanted us to compare the two volumes, but we didn't do it that way, so you just can totally blow this page off. So what that basically means is we see a difference between the measured and accepted of 0.05, but our plus or minus 0.007 is much smaller. It would have been better if this number was at least 0.05 or more, because then that means that we did a successful measurement, even if they are different like this. However, if we did a percent difference, we only get a 0.6%. So that's damn good. And so what it's basically telling us is that somehow we didn't get this plus minus correctly. That's no big deal. Okay, so that we've gone over in a lot of detail, and now I just went through a quick summary. So let's go back. Let's go to part 2. Now I reread the directions. And the directions really say you're supposed to have weighed the two of them before you submerged anything. And I suggested that you do it. Here, measure the combined mass of both in the air. And the group that gave me their data, it doesn't seem like they did it. Hopefully you did. So that we were asked to do 3 mass measurements, M1, M2, M3. So the first one was the two of them. It's going to give us the combined mass, actual masses. M2 is the apparent mass of the brass, because it's the only one submerged, so there's some buoyancy force, plus mass of the wood. And then M3 is going to be both of them submerged. So M3 should be the smallest one. At least we see that when the brass is submerged, it's bigger than when both are submerged. At the end of the day, keep in mind we want the density of the wood. So we can play a little game here. We know the mass of the brass itself, and we know it's submerged. So what that tells us then, that the F buoyancy on the brass is 43 grams, or the mass, the buoyant mass. So then if we take the M2 and we add the buoyancy mass, we'll get, this will give us M1. I don't know if we're going to need it, but at least we know now that both hanging in the air of 403, 1 submerged 363, 1 and 2 submerged 320. So that's great, and that's what we would have expected. Now maybe we'd like to have the mass of the wood, so we'll see. Maybe that's what we're going to do. But right now what I want is I want to get F of B on the wood in anticipation of this equation. And we see that if we take M2 and subtract M3, we will end up with M wood minus M wood, apparent wood, because the M brass apparent will cancel out with this M brass apparent. So we know then that the difference between an object's dry mass and its submerged mass is the mass buoyancy, and if we multiply it by the acceleration of gravity, like we see here, and I had to divide by 1,000 grams per kilograms to get newtons. So what we see here is the F buoyancy on the submerged wood block is 4.99 times 10 to the negative 1 newtons. Okay. So now we'd like to have the weight of the wood. So we happen to know, we calculated in M1, we know the mass of the brass. Where is it? Here. So if we subtract the two, we'll get the mass of the wood. And then we want the weight of the wood, so we divide by 1,000 to get kilograms. And then we multiply by the acceleration of gravity, meters per second squared. And so we get 3.87 times 10 to the negative 1 newtons for the weight of the wood. Now, notice that F of the buoyancy, the force of buoyancy on the wood is actually greater than the force on the weight of the wood. That's why the wood floats. So that's the condition. To make, for something to float, the buoyant force has to be greater than or equal to its actual weight. Now, generally speaking, you want it to be greater, because if they're equal, the thing will just barely float. And usually we'll want something above, we want something to be above the water in the real world, but still, if the two of them equal, it's going to float. Well, actually, if they're both exactly equal, it's called neutral buoyancy, and you should be able to push it down into the water, and it should just stay wherever you put it, which in principle, that practice is pretty hard to set things up that way. But if you know anything about scuba diving, that's why you have this vest around you that you can inflate and deflate. Anyways, now that we have all the things we need for this, weight of the wood, the density of water, and the buoyancy force on the wood. In this case, I can use grams per centimeter. Even though these are in newtons, the newtons cancel. So I don't have to use kgs per meter cubed, which, by the way, I goofed. It's not 1 kg, it's 1,000 kg per meter cubed. It doesn't seem to be too big of an issue, but we'll see in a minute. So anyways, we end up with a density of the wood, if I use these equations, that is 0.776 grams per centimeter cubed, which ends up being less than the density of the water, which basically is the condition. So any object that has a density less than water will float in water. So remember, we didn't have to do any error analysis, so that's that. Now, one thing now, let's take a look at the manual. Parent draw fair. Let's see. In determining the density, the buoyant force, we found subtracting draw all the. Well, you have all that. I guess I should post this PowerPoint slide so you can steal things. So you can do everything you need there. And now let's address number 2. And so what we noticed is that the wood weighs only 3.87 times 10 to the minus 1 newtons. So that means we only need an F buoyancy equal to that. So then we want to calculate what is the volume of H2O, what volume of water that weighs the same as our piece of wood. So we know that the weight of H2O is equal to the mass of the H2O times the acceleration of gravity, or if we just say the rho, the v, and the g, and once again, this is, I keep missing, I think that's equation 2. And remember, that's a definition. And, yeah. So the weight of water, weight of anything, that's always true. So we can, by plugging in numbers, because when we rearrange it, because we want to know what volume of H2O weighs that many newtons, and here's where I had to use rho at 1,000 kilograms per meter cubed, because we had to get the units correct. Oh, this is a conversion factor. Never mind. Well, let me see. Rho is 1,000 kilograms per meters cubed. Right, so we end up with a volume in meters cubed. And as we, I don't remember, I thought I wrote it up here, but let's just be safe. There are 1 times 10 to the 6th, if you can believe it, centimeters cubed to meters cubed. And the way you do that is that a centimeter is equal to 100 times 10 to the minus 2 meters. And if I cube that, I get 1 times 10 to the minus 6. So when I, in this case now, I multiply by 1 times 10 to the 6th, and I end up with 39.5 centimeters cubed. That's how much volume of water I need. So we know then that if I have a volume of any object multiplied by the density of that object, it's going to be the mass of that object. If we are very careful to specify that we're only going to submerge a certain part of it, and that volume that we're going to submerge is equal to the this particular volume. And now notice now it's a volume of H2O. And so we can multiply it by the density of H2O. And we'll also get the mass of the object because we specified that the particular volume of water is going to equal the volume of the object, the part of the object that's submerged. And we just showed this a little while ago on the previous page. But now we can see that these two equations are equal to the same thing. So we can say V object, rho object equals the part V submerged times the rho of water, and then we can just rearrange it to get V, so the V submerged, and that's just how much of it that's submerged, over V object equals these two densities. And notice that can also be equal to some fraction of so that ratio, we can call it the fraction submerged. And so that means that we can say that, oh, not that, we get rid of that. The fraction submerged, whatever that number happens to be, we multiply that by V object, we can get the volume submerged, if you like. That's maybe not too much of a useful number, I'm not sure. But as I said, this lab needed a whole lot of thought put into it, which I've now done, but we can't go back. So that, we've done what we had to do. You're not responsible for things that we didn't do, but now you have just about everything you need. There's no error analysis here, so we don't have to go through it. And let's see, what in determining the density of the wood, the buoyant, yeah, so again, I've given you those diagrams. I will publish this as a PowerPoint slide, so if I do that, you can go ahead and copy paste these diagrams. And you, I mean, I'd ask you not to just copy paste every single thing I did, but in fact, let's copy this slide and put it here, because I'm just going to, let's see, oh, I got this in eraser mode. I just want to double check. Diagram, okay, so these are all, you can play with these as you will. So I didn't really need to do that, but I'll just leave it there. So I'll save this. It's going to be a big file, guys. But, I just don't know how to squish down all the writing. But if I make it into a PDF, then you won't be able to copy paste diagrams or copy print. You know, I don't have to write a report for this. Okay, so that's it.